Hey everybody, it's Mr. Carr again. Today we're going to be looking at 6.5. This is going to be solving exponential and logarithmic equations here. Now, where this is a little bit different from before is that we're trying to solve for the exact value of like x in these kinds of scenarios. Some of them are a little bit more straightforward. So for example, in the first one, one strategy we can do is when we want to solve an equation as the variable as part of an exponent, we're going to use a logarithm of the same base unless the base is already the same. So one strategy, like with the first case, is if we already have base 3, then we can just kind of ignore the bases. Because the only way for 3 to the x minus 1 to be equal to 3 to the 4x plus 8 is if we kind of just ignore those two, and then x minus 1 has to equal to 4x plus 8. Okay? So now I can just solve this like a regular linear equation. So I'm going to add, well, actually, no, I'm going to do this. I'm going to subtract x and subtract 9 to both sides. So that's gone. I don't know why I did 9. I'll get ahead of myself, actually. Okay, let's try that again. Subtract 8 to both sides. So negative 9 is equal to 3x. So I divide by 3, and I get negative 3 for x. Okay? For the next case, we don't have the same base. Sometimes there are certain problems we can set them, like we can change them into the same base, but we can't do that here. So in this case, what I'm going to do is, because my exponent base is 4, I'm going to use log base 4, and I'm going to treat it like it's an operation. If I do it to the left side, I got to do it to the right side. Okay, so what really happens is this is going to cancel out, so x is going to equal to log base 4 of 10. So however you want to evaluate that, you can do change of base formula, or if you have the buttons in your calculator, you can just hit log base 4 of x. Either way, x should come out to about 1.66. Whoops, 1.66 when I get that. Okay. For the next one, we're going to treat this just like just like any other solving equations. I am going to undo my order of operations. So when I look at x is being multiplied by this negative 3. Then it's part of the e exponent or base e to that exponent, multiplied by 4, then subtracted by 7. So I'm going to start by getting rid of the 7. So we'll add that to both sides. So 4e to the negative 3x equals 20. Okay, then I'm going to divide both sides by 4, get rid of that part. And then here's our logarithm part. In order to undo this base e, we're going to use natural log. Okay. The inverse of this e is natural log to both sides. So that way that gets rid of that. So I'm going to have negative 3x equals the natural log of 5. Finally, I can divide both sides by a negative 3. Okay. Now I'm just going to write this out one time like this because x is equal to the natural log of 5 divided by negative 3. That's what I'm going to plug in my calculator. Okay. So I type in natural log of 5, take that divided by negative 3, and my answer will come out to about negative 0.54. Okay. So that's our basic idea here. There are other cases where we can kind of look for shortcuts. It's possible I could do log bases here, but the problem is at 64 and 8, they're different bases. But I can rewrite them with the same base. That will make things much easier. In fact, once they're the same base, I don't even have to deal with logarithms. So for example, since 64 is the same as 8 to the second power, I'm going to rewrite it like that. Okay? So that's our little trick we have here. We can rewrite bases into the same bases. Okay? So we just want to make them into the same bases as the goal. So 64 becomes 8 squared raised to the 3n power equals 8 to the 2n minus 3. From there, I'm going to use my exponent rules where it's 2 raised to the 3n power. I'm going to just multiply those exponents. So it's going to be 8 to the 6n is equal to 8 to the 2n minus 3. Okay, so from here, we're going to go ahead and just do our normal solving methods. So that means that 8s are going to actually cancel each other out. So I get 6n is equal to 2n, oops, 2n minus 3. And now I'm just solving a normal setup here. So I can do subtraction by 2n here. So 4n equals a negative 3. And then I divide by 4. So I get n is equal to a negative 3/4. I don't like how my 3 came out there. So let's try that again. Negative 3/4. Okay. So I'm going to do the same thing on the next one. 4 and 32 can be rewritten as the same base. I do not have a direct connection with 4 though. 4 raised to a power, if I do 4 to the second power, that's 16, 4 to the third power, 64. That doesn't work here. But both of them can be rewritten as 2. So 4 is the same as 2 squared. So it'll be 2 squared raised to the 3x power. And then 32 is 2 to the 5th, and that'll be raised to the x minus 1 power. From here, I'm still going to do the same multiplying exponent rule. So I have 2 times 3x is going to give me 2 to the 6x power. Here, I got to be careful because I'm going to distribute that 5. I'm still going to have to do 5 times x minus 1, but that's going to turn into 5 raised to the 5x minus 1, or sorry, 5x minus 5 power. Okay, yeah, write that a little better. 5x minus 5. Now that they're exactly the same base, we just simply cross this off. So that 6x equals 5x minus 5, and then I subtract 5x to both sides. So I get 1x equals a negative 5, and that's it. I'm done. So again, so our trick here is we can either do turn one base into the other one, so they're the same, or change both of them into the same base. That will make it easier to work with. Now that we know how to use logarithms to solve, we can revisit a story problem from before, okay? In the past, what we did with the zombie infestation problem was we use a guess and check, or we use like a table or a graph to find when, like for example, when the entire world's population of 7 billion gets infested. Okay, so recall from before that if we're increased by 87% per day, okay, so we start with 3 zombies, then that amount is going to equal to 3 times 1.87 to the t power. And in this case, t is going to represent days. Okay, well, technically I'm doing 1 plus 0.87, but let's just leave it as 1.87. So now normally, like I said, like we did before, we would have done it into a table or a graph. Now we can set this and solve it for exact value. So 7 billion, 1, 2, 3, 4, 5, 6, 7, 8, 9 is equal to 3 times 1.87 to the t power. Okay, so now I can do this. I can divide both sides by 3. Okay, so when I do that, I'm going to get, there'll be 2,333,000, or sorry, 2,333,333,333, and close enough. Okay, and that equals to 1.87 to the t power. Now I can do log base 1.87 to both sides. Okay, log base 1.87. Remember what that does is that cancels that out. So this is what I'm going to put in my calculator just like that. Log base 1.87, log base 1.87 of 2,303,000,000, blah, 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 blah. So when I do that, I get about 34.46 days for t. Okay, so now we can have an exact value versus like this kind of just like a rough estimate, basically. We can also use our logarithmic properties for solving methods. So for example, if we have log base 5 here, so this works same way as exponentials. If we have the same logarithm on both sides, we're simply just going to kind of ignore those and cancel them out. So 4x minus 7 will equal to x plus 5. Okay, let's do that right there. So from here, subtract x, I can add 7. So 3x is equal to 12. Divide by 3, and then get x equals 4. Okay, so when we do this, you have to be a little bit careful. We actually do want to still check our answers here, because with logarithms, we cannot take the logarithm of a negative number or 0. Because think about what that means. If I try to take the log of 0, then that means I'm implying that some base number, let's say log of 0, x raised to some value of x, sorry, x raised to some value would equal to 0. And I can't raise a power, like a base x to a power, and get to 0. It's just not possible. Same thing with a negative number. If this was a negative log of, oops, let's say log of negative 5, okay, if I take x raised to some power, I cannot get to a negative value either. So that's why I just got to be careful here. So if I, for example, plug this back in, that's 4 times 4 is 16, minus 7 is 9. So that turns into log base 5 of 9. Okay, When I plug it in here, that's 4 plus 5, that is 9, and I get the same thing. So it checks out, we're good. From here, log base 7 of x equals 3. Now, you can kind of just rewrite your logarithmic into exponential form. That's a possibility. You can just do that. But the idea is that if I think of this as what is the opposite of log base 7, it is doing an exponent with 7 as my base. So this will actually cancel it out. So x is equal to 7 to the third power. Okay. That either way, I'm either rewriting it in logarithmic into exponential form, or I'm just taking base 7 to both sides. Either way, I get to 343 as my answer on that one. Okay. Some more logarithms. So in this case, we're going to go ahead and just do the base 4. We're going to rewrite it using our base 4. So the idea here is that if I have log base 4, I'm going to undo that with the base 4 like that. So that means that's 5x minus 1 is equal to 4 to the third power. Okay, so that means 5x minus 1 is equal to 64. Add 1 to both sides. 5x equals 65. And then I divide by 5, and I get x is equal to 13. Okay, quick check. Does it work? That's 5 times 13 is 65. Minus 1 is 64, so we're good. Next one here. Natural log of x right here. I want to first undo everything else that I can. So I'm going to start by subtracting 2 to both sides. So that 10 is equal to 5 times the natural log of x. I'm going to divide both sides by 5. So 2 equals the natural log of x. And remember, the natural log, the inverse of that is e, because natural log is log base e is what it really is. So that means I'm going to basically take e to both, like base e to both sides. That way that cancels that out. So I have e squared is equal to x, and I plug that in my calculator. So that comes out to about 7.39 for my x value there. Okay. All right. Sometimes we have to actually use our logarithm properties to condense first before we can do any solving. So for example, here, if I take the log of 2x plus the log of x minus 5, and that equals 2. Well, the first thing is notice how it's addition here. The addition means I can go ahead and do log of 2x times x minus 5, and that will equal to 2. Well, now I can distribute the 2x here like that, and I'm going to do two things at the same time. Since this is log base 10, I'm going to take base 10 to both sides like that. That way that goes away. So 2x squared minus 10x is equal to 10 squared, which is 100. So I'm going to solve this out as a normal quadratic. That means it's going to be 2x squared minus 10x minus 100 equals 0. I can divide everything here by 2, so I get x squared minus 5x minus 50 equals 0. And then this is pretty good for factoring. So to multiply to negative 50, add to a negative 10 or negative 5, that's going to be x minus 10 and x plus 5. Okay, and so that means that's going to give me x is equal to, x equals 10 and x equals a negative 5. But make sure you double check for that extraneous solution. And so what I mean by this case is if I look at negative 5 and I plug it in here, for example, or here, it doesn't really matter. If I take the log of 2 times negative 5 plus the log of negative 5 minus 5, then I'm taking the log of negative 10 plus the log of negative 10. I can't take the logs of negative numbers. Either way, it doesn't work. So that means that I'm going to cross that one off as extraneous. So I only have one good answer here, and that is going to be x equals 10 in this case. All right. And that's a lot of solving methods there. We got a lot going on with that one. So just make sure you're always trying to get it down to as simple as possible with the logarithms or the exponential bases. And then it's just a matter of kind of undoing our logarithms with exponents or undoing our exponential with logarithms. Okay. But that's it for today. So take care, everyone.